Hi there, welcome to the second half of what should have been today's lecture. I had to speed things along. I think I talked about IR a little too much, but I think it's really important to talk to you about chemical equivalency and predicting where proton NMR absorptions are expected, how many there are, and what they're worth. So first I'd like to say that I hope the audio turns out good. I used to have a really nice microphone that was connected to some headphones, but unfortunately there is a monster in our midst, and this poor little guy decided that he would chomp on my nice headphones with microphone. Anyways, this is the version that I wanted to go over in class today. You got the short version. Here is the slightly longer version. So here are some simple examples of compounds that have only one type of proton, which means they're only going to have one signal in their NMR spectrum. And we want to have an idea of why there's only one signal, how many protons each signal is worth, which may be obvious, and then what's its chemical environment, because that's going to tell us where it shows up on the x-axis, or in more technical terms, what is the compound's chemical shift in the proton NMR spectrum. So the reason I left a lot of space is because there's kind of a specific way to go over and determine whether each of these protons are actually the same or if they are different. Now, these are examples where it may be obvious that those could be considered to have the same chemical environment and that they're equivalent, but I'm going to start with simple examples, and I hope that you pick up on this quickly. So what we do is we look at the Lewis structure of each atom, or each molecule. I'm going to do this twice. So I'm going to kind of highlight this. I think I can do a little copy and paste. Okay. So the question is, if we were to take any two protons, let's say like this proton and that proton, the question is, are they the same? Do they have the same chemical environment? And the way that you can do that is to replace this proton with some other group, just say like an X. I don't even want to give it an actual atom. So let's say that group is an X, and we wanted to know if this proton was the same or not. So we would replace on a separate drawing of that structure, that molecule with an X. And we would figure out, are they the same compound or not? And in this case, they are the same. You notice that it's still, the X group is attached to it's attached to a carbon, which has 2 hydrogens, and that carbon is attached to another carbon, which has 3 hydrogens. So again, the X group is attached to a carbon, which is attached to another carbon, which has 3 hydrogens. So small molecule, but that's the way you do it. If you're not sure if any two hydrogens are the same or different, you replace one group at a time, one hydrogen at a time, with, in this case, an X, just something else. And you could do that very same thing with this example of cyclohexane. Sorry, let me back up. That means that they are all equivalent. Here, these are all equivalent protons, and that's why you had only one signal. So now we can do the same thing. We have all these different protons in cyclohexane. So we have the 2 up there. Any hydrogens that are attached to the same carbon are going to be equivalent. I hope you can see that they do have the same chemical environment, but you can use the same trick that we had done there before to figure out that they are definitely the same or not. So let's say we're going to draw our cyclohexane molecule. We'll draw it twice. And you're trying to figure out if the 2 hydrogens on that top carbon are the same or not. So if we were to draw one where it's like a X group here and then a hydrogen versus another where this is an X group here and that's a hydrogen, I hope you can see that these 2 are the same, which explains why those 2 protons are equivalent. I'm going to do same idea. Let's say we're not sure if the proton on the top and the proton on the bottom are the same or not. So let's say, we're trying to figure out, is that guy the same as the one that's up on top? You would replace the one on the top with an X and the one on the bottom with an X. And once again, you see that those 2 compounds are in fact the same. Great. So now we move on to this methyl ether example. I'll just write that, methyl ether, so I don't keep saying it wrong. This is methyl ether or dimethyl ether, same deal. And we'll draw its Lewis structure. all of the hydrogens in the whole molecule are equivalent to each other, we can use our, not really a trick, it's just the way to really do it, to figure out if any two protons are the same or different. So here's two drawings of the same molecule. So let's ask ourselves a question, are these two the same? They're connected to the same carbon, so the answer should be yes. I want to teach you this technique because it's going to apply to more complicated examples. So let's replace that hydrogen and that hydrogen with X groups here and here, and you see that those two protons are the same because those two, if that were an X group, that would be the same molecule. You could go ahead and do same thing if you were trying to figure out if that hydrogen and that hydrogen are the same or different. So we're going to replace that hydrogen with an X and that hydrogen with an X. Okay, so let's put an X group here and an X group there. Those two are once again the same molecule. If you rotate one, it looks like the other. And that's what helps us determine that all of the hydrogens in methyl ether are all equivalent. They're all the same chemical environment. So there's one signal in the NMR spectrum. So then we will go down to the next question. How many protons is each signal worth? And that's just asking the same question because there's only one signal. How many hydrogens are in the compound? Here we have 6 hydrogens in ethane. We have 12 hydrogens in cyclohexane, and we have 6 hydrogens in methyl ether. So 12 hydrogens. So one signal could be worth a lot of different hydrogens. You'd need some other information to figure out that just from an NMR spectrum. But cool thing that you can get is its chemical environment. We did this in class, but I think this is important. This is going to help us understand where we actually can expect them on the x-axis. For the example of ethane up above, you have a hydrogen attached to a carbon, which is attached to another carbon, and that functional group is actually not a functional group really, it's just an alkane, nice and boring alkane. The next one would be the same, actually. Any hydrogen on cyclohexane is just bound to a carbon, which is bound to another carbon, and there's nothing interesting going on, it's just an alkane. The last example is an ether, it's dimethyl ether, and for each of those we have a hydrogen attached to a carbon, and that carbon is attached to an oxygen. So again, that's an ether. So this is the kind of formula that I'm using because that's going to be what we see in our table of values to figure out where it actually lies on the NMR spectrum. So I'm going to take you there so we all know where to find these things. So I'm just going to switch apps here and go to the class website. This is at the very bottom of the Chem 8M website, and here are the NMR intro tables. So there's a couple of figures in the front that could go over what resonance frequency actually is, how it kind of like flips the spin of the atom. We talked a little bit about that, and I had some pictures here really just so you can see some of the inner workings of the instrument, but mainly what we care about is what you see on the printer display, what actually the peaks are. That's there if you're interested. There's a couple little reminders here of what downfield and upfield are with regards to shielding and deshielding. Here you see some examples that I'm actually going to go over a little bit later in this video. It's just some samples of what NMR spectra look like. What I really wanted to get to here is page 3, but I wanted to take you there where you can see where different protons show up on the x-axis depending on what functional groups they're bound to. And I have 2 different pictures. I like this one here because it gives you a relative idea of where the functional groups show up with kind of like little snapshot pictures of the simple version of the functional group. But down here, you have that same exact information, but it's just given in table format. So we could actually look up, for example, where ethane or cyclohexane would show up. We already noted that they were alkanes where you have a hydrogen bound to a carbon, which is then bound to another carbon. And we can see that little area between 0.8 and 1.9 is where we would expect both of those compounds to show up. So I'm going to switch back. Both of these, once again, would show up between 0.8 and 1.9 parts per million. And within this video, I'm going to also explain those units as well. So a bit different for the ether. I'm going to scroll back. We're looking for a hydrogen connected to a carbon that's connected to an oxygen. So we're looking for an ether functional group. I can't actually draw on this because it's a web page. It's not my annotating thing. But right there, like middle-ish bottom, we see a section on alcohols, esters, and ethers where there's a hydrogen that's in bold bound to a carbon bound to an oxygen. And that's going to show up between 3.2 and 5.3. Okay, so that's where we'd expect diethyl ether to show up, dimethyl ether. And I have that on the second page, and you guys can see all that. What's happened before page 3 in the lecture webcast. So now we're kind of caught up. This is what I did. Sorry, this is the section of the notes that I went over in lecture. But as you can see, this is a really different, at least for the top, it's kind of a different approach in terms of replacing one hydrogen with the X or not. So I want to apply that to a more complicated example, and that's this guy down here. It has a lot of interesting functional groups on it, and we want to figure out how many proton NMR absorptions are expected below. Now, the reason I have multiple drawings of the same molecule should be a little bit more clear now. It's because I want to give you the opportunity to actually draw these structures with different groups on them to see if certain protons are equivalent or not. So the first thing that we did, we kind of categorized them. We looked for CH3 groups. So we had 2 different CH3 groups. And we just kind of made that known to start off, but we can get a little bit more into it since I have this time. We had 2 CH3 groups. In order to actually use that thing above, the technique, we would replace one of the groups. So let's say that both of those just have 2 hydrogens now. We replace one of the hydrogens with an X group. Oh, sorry, I did that wrong. So this is supposed to stay. This one's supposed to stay a CH3. And then let's say this one over here is now a CH2X. So I hope that you can look at these 2 compounds and see that they are for sure different compounds. I think it's important to see the examples where they're different because up above they were all the same. So up above, all the times that I did that was the same. But now those are very different compounds, which further confirms that those 2 CH3 groups are non-equivalent. They are different. The easier way of going about that might just be to say that, hey, this methyl group right there, or maybe let's do it over here, this methyl group right here has an oxygen near it. This methyl group right there does not. So those are different. Okay. Great. So I'm just going to call those on this cleaner version over here. I'm going to call that signal 1 and signal 2 only because those are the first 2 that we identified. This has nothing to do with where they actually lie on the spectrum. I just want to keep track of how many there are. Okay, so let's restart. Okay, so just clean those up. Now let's go to the CH2s, the methylenes. We have only one. Let's see how many CH2s. There's actually one CH2 group. This guy right here has 2 hydrogens. Since those are attached to the same carbon, they should be equivalent, but the way that we figure that out is by replacing one hydrogen at a time with a different group. So let's say on this first example, we're going to replace the hydrogen with an X group, and on the second one, we'll replace the other hydrogen with an X group. Those 2 are the same, which means that those 2 hydrogens are equivalent, and that here, this accounts for just a 3rd signal, as opposed to being a 3rd and a 4th signal for the 2 hydrogens. Actually, what I should be doing here is making a little note. That blue signal, as I call it, is a 2 hydrogen signal. Let me get rid of the apostrophe S. It's a 2 hydrogen signal. Each of the ones that were in red, those were 3 hydrogen signals. Okay, so we have 3 signals, and then I'm kind of keeping track of the ratio of peak areas. That maybe should be something I do more towards the bottom, but it will be already answered for us. So that's what I'm doing here. This is going to give us the ratio of peak areas once we integrate them, but we can kind of do this all at the same time. All right, so the fun really begins when we look for all the different CH groups. So now I'm going to add in 1 hydrogen at a time. So the rest of the carbons in the molecule have only 1 hydrogen attached, with the exception, before I get into it too much, of these two carbons have no hydrogens, so we would expect no signal for them because there are no hydrogens. That's kind of all there is to it. Anywho's, so we're trying to figure out if these two hydrogens are the same or different. We can do the same thing for all of these, but I'm going to start one at a time. I'm going to first compare if those two are the same or not. And we do that by replacing one hydrogen with an X group. So let's say on one of them, yeah, it'll be an X group here, X group here. In order for this to actually make sense, I need to remove these, and I'm trying to figure out if those two are the same compound, because you can do some rotation, and there's symmetry in the molecule, so even better, we see that there is symmetry here through the molecule. So we find the same thing happening on either side because of the substitution of that ring. So these two, as drawn, if they're X's, are the same compound, which means that those two CH groups that are right next to that ether group are actually the same hydrogens, or rather they would account for one signal. So this would be our fourth signal, and this accounts for two hydrogens because we had two equivalent protons. So that's important. I want to make sure that's clear, that the two hydrogens that are next to that methoxy group are equivalent. This guy and this guy, these are equivalent protons. Great. Now we move on to the next set of CH2s. We have these two hydrogens here and here. And these two hydrogens have the same relationship to the other groups on the ring. And once again, we have this plane of symmetry. So they're both right next door to that alkyne substituent, and they're 2 carbons away from the methoxy substituent. So those two are actually equivalent protons. And once again, the way that we work that out is we replace one at a time with an X group. I'm going to clean up the rest of this stuff here, one second. So here we go, replacing one at a time with X and X, and we see that those two are the same compound. We have some rotation around the molecule here where you can see that, or rather like you can flip the molecule and you can see that these two, once again, are the same compound. So those two hydrogens that I had labeled in blue, those are equivalent signals or equivalent protons. So there it is, hooray, they're equivalent protons. Now we want to make sure of the relationship between those protons and the ones we had labeled in green. And it turns out these sets of protons, these two, are non-equivalent. They are different. Now that may be something that's clear just by looking at the structure itself, but the reason that I'm putting this video together is so you can actually use that technique to figure out unequivocally whether or not they are the same. So here we're going to clean this up. One second. So I just simplified, letting me replace, we'll call it the blue line we'll replace with an X, whereas over here we'll replace the green line with an X. And I hope that you can see that these are different compounds. These are different compounds because here we have the X group, it's 2 carbons away from that ether group, whereas here the X group is now 1 carbon away. Because those two are different, we then call this CH set of CHs a new non-equivalent signal. It accounts for 2 hydrogens because we do have equivalent hydrogens, right? So these guys are equivalent to each other, but these 2 hydrogens, point out, these 2 sets of hydrogens are non-equivalent, meaning they do not have the same chemical environment, so they'll be showing their own unique signals in the NMR spectrum. So that takes care of 2 CH signals, but there are still 2 more carbons, 2 more sets of hydrogens we have yet to explore, and those are the vinylic protons. So I'll write that down. Those are vinylic protons. They are hydrogens connected to carbons that are involved in an alkene. So the question is, are they the same? And so what we do is we replace one hydrogen at a time, mirror and mirror. So in different examples, we'll place an X here and an X here. We ask ourselves, are they different compounds or are the same? I hope we all agree that these are indeed different compounds. We have the X group here right next to the arene group, whereas this one is 2 carbons away. So we do have 2 additional CH2 signals. So we'll call this signal 6. Signal 6 accounts for only 1 hydrogen. And then finally, we have signal 7. So there's 7 signals total. That's actually the answer to this main question, that there are 7 signals, and signal 7 here accounts for 1 hydrogen. So that's a lot of different things that we have there, 7 signals. Each signal is worth a certain number of hydrogens. And so that's what we mean by the ratio of peak areas. So how many hydrogens is each signal worth? What's going to be the relative ratio of each of the signals on the proton NMR spectrum? And it goes like this: 3 to 2 to 2, those are the aromatic protons. We have 1 to 1 for these vanillic protons. We have the CH2 group, so 2 hydrogens, and then that last methyl group. So you're going to have 7 signals, and when you integrate those peaks, or rather when the instrument integrates the peaks for you, that's the ratio that you'll get. And because you have 1 hydrogen signals, those actually equate to 3 hydrogens, 2 hydrogens, 2 hydrogens, 1 hydrogen, and so on. Great, so that's what I want to say about that. Now, we fill in this last thing. So this is the other way to get to 7 hydrogens, or 7 types of hydrogens. We said that there were 4 CHs, and that was the way that we did this in lecture, that we got a total of 7 signals. Now it's time to approximate the chemical shift for each type of proton, which means we need to figure out the chemical environment for each signal. And we're going to do that one at a time. So we have this set of protons right here. Those are hydrogens connected to a carbon, connected to an oxygen, and that functional group is an ether. We don't go so far as to say that that oxygen is then connected to an arene group, because then we start to get too far away from the hydrogen. So notice we've gone like 2 bonds away. These proximity effects are important. We'll see the limitations of that. So we're looking for the ether. I'm just going to save some time. We already had the range for the ether there on the top right is 3.2 to 5.3. So that's about where you'd expect this to show up, 3.2 to 5.3 on the x-axis, and I'll explain parts per million on the next page. I know you can't wait. Next, we have all of these hydrogens. All of those red hydrogens, they're in the aromatic range. To be a little more specific, these guys are hydrogens that are connected to carbons that are in the aromatic ring, or are in the aromatic ring. So I'm going to switch over to the table. Remember, these are online. And we see that there are 2 different places in the table where you'll find aromatic compounds. You'll find one in the middle. Notice that it has the one in the middle with a little B next to it, has AR connected to an aromatic ring, connected to a carbon, connected to a hydrogen. But our hydrogen is directly connected to the aromatic ring. So we want to use the one on the bottom, like the third from the bottom, aromatic compounds, ARH. And that range is 6.5 to 9. So that's where we expect to find these protons. We then have this hydrogen here. Let me jump back. So there are 2 distinct signals. These are different, and we'll talk about how, or the other effects, like how close the other groups are to that methoxy group. There are still 2. We have 2 aromatic signals that are both in the 6.5 to 9 range. So they just are in the same range, right? Big range. Okay, so now we're at the one that I drew in blue, this vanillic proton, vinyl. It actually can fit into a couple different categories. So this is where you'll be looking to see if it's like, there's groups 2 or maybe even 3 carbons away. So we're going to categorize this hydrogen is connected to a carbon, which is involved in an alkene, right? So that's this carbon connected to that carbon. But the carbon here that is directly connected to the hydrogen is actually connected to an arene group, or rather an aryl group. an arene. So it fits into two different categories because it's next to an aromatic group and an alkene. So it's going to fit two categories, which just means it's going to be even more de-shielded. I'm going to erase this word vinyl. We can fit it into two categories, but we're going to choose the higher one being representative. So let's go back to the two categories. We're looking for an aromatic group, noticing that now it's the it's the hydrogen attached to a carbon connected to an aromatic group. And then the second category is the hydrogen connected to the carbon of an alkene. Okay, so the first group we saw earlier in the middle, the aromatic compounds with a little b, is when the hydrogen's connected to a carbon connected to an aryl group, and that range is between 2.2 and 3. Let's translate that. So that range would be 2.2 to 3. Let's look at the other group, or the other categorization, where the hydrogen's connected to a carbon of an alkene, and that is 1, 2, 3, 4, 5, 6 from the bottom, where the hydrogen's directly connected to that alkene, and then we have that range is 4.5 to 8.5. Pretty big difference. 4.5 to 8.5. Okay. All right, so this is the higher range. This is going to have a bigger effect. These effects are, however, additive because we have this de-shielding effect as well, the proximity to the arene group. It just means that it's going to be, that proton in particular is likely to be on the higher end of that range. Great. All right, so then we move on to our next proton, which is also another vinyl proton. It's a hydrogen connected to a carbon, hydrogen connected to a carbon that's involved in an alkene. It's too far away from the arene group to have a huge effect. As you learn more about proton and NMR, you'll learn how, I'll teach you later on how the effects actually do make a bigger difference. But for right now, we're just trying to do simple categorization based on the table that I've given you. So here we're going to see that we have 4.5 to 8.5 is going to be the general range for that proton. Continuing on, we have these two protons here, and these two protons actually do fall in the alkene category. They are allylic, meaning they are hydrogens connected to carbons that are then involved in an alkene. So we can find those within our table. It's still in the alkene category. So if you go one, so there's TMS, alkanes, amines, alcohols, and then alkenes with a little a, and that a goes for allylic. It's a hydrogen connected to a carbon connected to an alkene. The range is 1.5 to 2.6. That's where you'd expect it to show up. So you can see a real big proximity effect. If that hydrogen is right next to that alkene, it is way more de-shielded. Electrons are being pulled away, and it's kind of more naked and less protected from the magnetic field. Whereas in the allylic position, much less de-shielding going on. So we see a much lower chemical shift. And then let's see if we can sneak in this one here. This is a CH3 group. That's just an alkane. You can just like zoom in. Okay, so that alkane group is going to show up somewhere between 0.8 and 1.9. And that's where they all show up. That's how you use the table that, once again, is on the CHEM 8M website. And I hope that was helpful to you. Let's just take a moment and marvel at our work. Ooh, we have 7 different signals. One of them is going to show up between 3.2 to 5. Another one's going to show up on the higher end of 4.5 to 8.5. Another one's going to show up between 1.5 and 2.6. Another one there between 4.5 and 8.5. One is very shielded in the alkane range. And then we have 2 peaks in the aromatic range, 6.5 to 9. And that's 7. Great. Okay. So now we want to give a little bit more background on what the parts per million is all about, some other little details that I haven't quite gone over. I wanted to really focus on the ideas behind chemical shifts and how you actually use those tables and really how to do your pre-labs. So here's what the chemical shift is. It's a shift relative to TMS. This is tetramethylsilane. It is the most shielded molecule that we could come up with as scientists, as chemists. And it has a 0 chemical shift. And that just means that it has, so it's very shielded, and each of those protons resonate at a magnet, or resonate with the magnet at a relative frequency of 0. Once again, that's our standard. So this ppm, parts per million, just by definition, doesn't actually have a unit. So what we're doing, clean this up here. What we're doing is should be a hertz up here. That's the frequency in hertz or cycles per second. What we're doing here in this example is we're showing how tert-butyl acetate, so this here is tert-butyl acetate, it is analyzed by proton NMR as follows. It's dissolved in a solution of CdCl3. This is deuterated chloroform, deuterated. It's deuterated, meaning that, chloroform is usually CHCl3. If you were to just put CHCl3 in there, all you would see is this proton. It would just overwhelm your spectrum. But that proton can be easily exchanged with deuterium. There is a very, very small amount of CHCl3 left over. So pretty much any NMR spectrum that you would be seeing, with the exception of this example, you would see a peak for CdCl3 show up at about 7.6 parts per million. So pretty much every other spectrum that you'll see in this class, if you see a peak at 7.6, it's not for your compound, it's actually due to your solvent, right? So this is, once again, the solvent that doesn't interfere. It's spiked with a very small amount of TMS so that this peak is very small and doesn't really inflate your spectrum and make everything else seem really small by comparison. But we use a chemical shift as opposed to giving the units in hertz so that we can run the sample on multiple instruments. So the example below shows that we could take the same example, the same compound, on 2 different instruments, and we end up with the same chemical shifts for both. So here we go. We have, okay, so here's tert-butyl acetate. We have a 3 hydrogen signal and a 9 hydrogen signal. All 9 hydrogens in the tert-butyl group are equivalent. So we can see over here that equates to a 3 and a 9 hydrogen signal. Now on this is the 60 megahertz. Yeah, this is the 60 megahertz instrument. That's just the maximum operating frequency of the instrument or of the magnet. The actual resonance frequency of the actual protons in the molecule are a millionth of that operating or of that resonance frequency. So very, very, very small. When I called atoms mini magnets, I meant they're like really, really miniature small magnets in comparison to this big hunk of metal. Not really all metal. Anyway, what we're going to do, we're going to calculate the chemical shift. And this is starting in frequency, starting in units of hertz. So the actual chemical shift, often abbreviated with this delta symbol, is equal to the relative frequency relative to TMS. So it resonates at a frequency 87 cycles per second greater than tetramethylsilane. We put that over 60 megahertz, the maximum operating frequency of the instrument. The units of hertz cancel, so what we're actually left with is a mega, and the mega stands for a million. And since it's on the bottom, when we do this whole situation, we get 1.45, and then our unit, it was actually unitless, so our unit is actually over 10 to the 6. And that's really all parts per million are. I'm not sure I defined that up above, but ppm, it's a misleading arrow. ppm, this is parts per million. To put it a little bit more literally, you could say, how many parts do you have over 10 to the 6 or a million? This could be expressed as 1.45 times 10 to the negative 6, or much easier, 1.45 ppm. You see this is right about where it shows up here. This is 1.45 0.45 in terms of parts per million. Now, since I'm telling you that it should be, that chemical shift should be the same no matter the instrument, we should already know the answer to this next one. This next spectrum here was run on a 200 megahertz magnet. It has a relative chemical shift, relative resonance frequency of 290. So if we put 290 hertz over 200 megahertz, we get 1.45 over 10 to the 6, which is exactly the same thing as 1.45 parts per million. So really, parts per million is not a unit. It is a relative number. It's sort of like a ratio, but we can just call it a unit because it looks nice and it's easier to call it a unit. And that's what the ppm is all about. Great. So their last example that I have below is actually kind of a summary and a little bit of a look ahead to the future. It's how could we use proton NMR to determine or confirm chemical structures? I've alluded to this in lecture, but I wanted to show you a slightly more complicated example to put together the main components of today's lecture being a chemical shift and integration. Splitting is something that we'll talk more about in a future lecture and beyond, but it's here, and I thought it'd be a good thing to start talking about. So let's sort of pretend like we don't know this structure just a little bit and see how much information we can get just from these signals, and I'm going to teach you a little bit more about splitting. So let's pretend that we don't know what that is. What we have first, I like looking at the integration first because that's pretty relatable. The 2 in this case could stand for 2 hydrogens, and each of these is 3. Now the integration is not always perfect, so sometimes you get 1.97 or maybe it would be 1.9, but it's good enough to round up to 2, and typically you're given more information, like you already know what the structure should be, or you have the chemical formula from another type of experiment. So that's telling you that it could be, this could be a CH2 group, this could be a CH2 group, this could be a CH3 group, and that could also be a CH3 group. Okay, so that's what it tells you. We have some other information. Let's say we took an IR spectrum, and it told us that we had a peak around 1700. And 1700 should be screaming carbonyl. So that tells us that we have proximity to a carbonyl, and you know, we at least have 1 oxygen there in the mix. So we would need to know some other information. We'll notice here that at 4 parts per million, we must have an electronegative atom attached to that carbon. And since, you know, once again, we do know the actual structure right now, I'm going to kind of go back and forth and show how we know what's what. So since this is connected to 4, or sorry, this shows up at 4, this is very de-shielded. That must mean, once again, that that carbon is attached to an oxygen. I'm going to continue on and play with the splitting patterns and make a little bit more space for myself. So splitting patterns, here's the deal. The rule for splitting is the n+1 rule. And this is the actual signal splitting. You'll notice up here, this signal has only 1 peak in that signal, and that's because it doesn't have any neighboring hydrogens. When you do have neighboring hydrogens, they split via the n+1 rule. Now this means if you have hydrogens next door, and it has to be just next door, then that is going to split the 1 signal. So instead of this being 1 signal, 1 peak rather, it's actually split into 4 peaks. And we call those 4 peaks a quartet. The quartet would be the total of the n+1 rule. So that means that n+1 was equal to 4. If we solve for n, we see n is 3. So the number of neighboring hydrogens was 3, meaning this CH2 group must be next to a CH3 group. So we can try that again because we see we have yet another quartet on our next peak here, our next signal. And then again, just kind of roll with this to the best of your ability. So in our next one, we have a chemical shift. Let's say it's around like 2.2, 2.3. And this is what we get when we have a carbon that's next to a carbonyl. And you're welcome to check that out on your table real quick. So we can see carbonyl compounds kind of in the middle and the top, where we have a hydrogen connected to a carbon of a carbonyl. That comes in a range of 1.9 to 3.3. Now, as you may be thinking, that's kind of a lot to put together. This is something that comes through experience and also by knowing what you're looking for. So let's say in this in this particular spectra, you were just told, it would be really helpful if you were told some way, shape, or form that this was an ester functional group. So that would give you an indication that this set of hydrogens here, because they have a chemical shift around 2.3, it's next to that carbonyl. All right, so now we can play with the splitting. We see that this is a quartet, which means it is split by 3 hydrogens. We have a CH3 group next door. So look at that. We've identified this CH2 group right there. This is the signal at 2.2 or 2.3. And we've identified this CH2 group. This is the one that showed up at about 4. Great. Now we have our remaining CH3 groups. Let me clean this up a little bit. We have our remaining CH3 groups, and both of those CH3 groups, these are actually 2 separate signals. These are both triplets. So in a triplet, that means n plus 1 equals 3. So 3 peaks goes with a triplet. So then n, we solve for it, becomes 2. If it's a triplet, that must mean we have 2 neighbors. So each of these methyl groups are connected to CH2 groups, which is what we actually see in the known compound, which is why it's useful to learn knowing the actual answer. These are 2 CH3 groups. They have a very small difference in chemical shift. You can see this one here is a bit more de-shielded, and that is likely because that one is closer to the oxygen, right? So this is closer to oxygen, which means it's going to be more de-shielded. This one is farther from the oxygen. No, other way. Farther from the oxygen, which means that it is the one that is closer to the carbonyl. And I hope that was useful. Remember, this last portion about splitting, we're going to be talking about in future lectures. This is just a little bit of a recap of stuff, and also giving you a real glimpse into how NMR can be used to actually figure out the full chemical structure of a compound, given little puzzle pieces of integration, chemical shift, and eventually splitting. Once again, thank you for joining me. I hope you all found that useful, and I hope you have a wonderful weekend.